Welcome back to Refinery Pro. I'm your host, Manoj Kumar, and this is third part of classification of refractory materials. In the first two parts of this episode, we explored classifications based on physical form, shaped refractories and unshaped refractories. In this part, we'll move forward and look at other important classifications, those based on chemical properties, chemical composition and method of manufacturing, etc. Whether you are an engineer planning a new project or maintaining existing equipment, understanding these classifications is essential for choosing the right refractory material for the job. So, let's dive in and begin exploring the next set of refractory classifications. Let's understand classification based on chemical properties, how refractory materials react in different chemical environments. This is a critical factor in material selection, because choosing the wrong chemistry can lead to rapid failure. Refractories are divided into four categories based on chemical behavior. Let's start with the first category, that is, acidic refractories. These are made mostly from acidic compounds like alumina and silica. In other words, alumina silicates. Here's the key point. Acidic refractories resist acidic slags and acidic furnace atmospheres very well, but they are easily attacked and corroded by basic, alkaline materials. That means acidic refractories are used specifically in areas where both the slag and the atmosphere are acidic. If you use them in a basic environment, they'll fail quickly. A common example is glass melting furnaces, where the slag environment is acidic. In such cases, acidic refractories are the right choice. Next, let's look at basic refractories, the counterparts to acidic refractories. They have completely different chemical characteristics and applications. Basic refractories are made primarily from basic materials like magnesia, MgO, and sometimes chromium, CrO. Their key property is, they are attacked by acidic slags and acidic environments, so they are not suitable for acidic conditions. However, they are highly stable in alkaline environments. They resist alkaline slags, dusts, and fumes at high temperatures, which makes them reliable where basic conditions dominate. This is why basic refractories are so important in furnace linings for steel-making operations, where the slag is predominantly basic. Common examples include magnesite, dolomite, chromagnesite, and forsterite, which is a magnesium silicate material. For steel furnaces and other applications with basic slags, basic refractories are absolutely essential. Now let's look at the third category, neutral refractories. These materials have unique chemical properties that make them especially versatile. Neutral refractories are chemically stable to both acids and bases. In other words, they resist attack from either acidic or basic materials. This means they can be used in environments where the slag or atmosphere is acidic, basic, or even when conditions keep changing. Some common examples include carbon and graphite, which are extremely inert and react with almost nothing. Chromite refractories also fall into this category, as do high-purity alumina refractories. The trade-off for this versatility is cost. Neutral refractories are usually more expensive than acidic or basic types. But in applications where conditions are unpredictable or where reliability is critical, the investment is often justified. They are also preferred in industries where contamination must be minimized, such as high-purity ceramic production. So, neutral refractories give you flexibility and reliability, especially when operating conditions are variable or demanding. Finally, let's talk about special refractories, the highest performance tier of refractory materials, designed for the most demanding applications. These are premium materials, manufactured using synthetic fused or sintered grains that are completely free from impurities. The production process is carried out under highly controlled conditions to ensure absolute consistency and purity. Because of their exceptional properties, special refractories are used in critical applications such as the construction of crucibles for ultra-high temperature processes, key furnace components where failure simply cannot be allowed. Research and development environments where purity and performance are essential. Examples include ultra-pure zirconia, ultra-high purity alumina, and other specialized compounds tailored for specific industrial or research needs. Yes, they are expensive, but when nothing else will work, special refractories are irreplaceable. They provide the reliability and performance required in the most extreme conditions. Most petroleum refinery process units, such as furnaces and heaters, reformers, hydrocrackers, FCC units, sulfur recovery units, etc., operate in an environment that is generally neutral to mildly acidic. This environment is characterized by combustion gases, carbon monoxide, carbon dioxide, sulfur dioxide, sulfur trioxide, nitrogen oxides, sulfur-bearing atmospheres, hydrogen sulfide and sulfur dioxide, reducing and oxidizing conditions depending on the unit and presence of hydrocarbons, coke, and metal dust. Strong basic slags, like those found in steelmaking, are typically not present in petroleum refineries. Hence, neutral refractories are predominantly used in petroleum refineries. Let's think deeper that why neutral refractories? Because neutral refractories are chemically stable in both acidic and basic environments, resist sulfur attack better than basic refractories, perform well under thermal cycling and reducing atmospheres, offer good mechanical strength and erosion resistance. Common neutral refractory materials used in petroleum refineries include high alumina castables and bricks, low cement and ultra-low cement castables, alumina-based erosion-resistant castables, alumina silicon carbide castables, especially in FCC units, mullite-based materials. Now let's move on to another important way of classifying refractories, by their chemical composition. This is perhaps the most detailed classification system, because it identifies the actual mineral constituents that make up the refractory material. According to chemical composition, refractories are divided into 9 distinct groups. Each group is defined by its primary chemical components, and those components directly determine the material's properties and where it can be used. Why does this matter? Because chemical composition directly affects how the material reacts with the furnace environment, its maximum temperature capability, its mechanical strength, its resistance to thermal shock, and its compatibility with the process materials. So, understanding chemical composition is essential for selecting the right refractory for the job. With that foundation in place, let's now examine each of the 9 chemical composition categories in detail. Let's begin with the first group, silica refractories. These are made up of silicon oxide, also known as silica. They can be produced in 2 ways, from naturally occurring quartz minerals or from synthetic fused silica created at very high temperatures. Silica refractories have some unique properties. One of the most interesting is that they actually become stronger as the temperature rises, up to about 1650 degrees Celsius. This is often described as brick above brick strength. They also have excellent resistance to acidic slags and acidic furnace environments. But there are limitations. Silica refractories are vulnerable to rapid cooling or thermal shock. Sudden drops in temperature can cause spalling and failure. They are also easily attacked by basic slags, so they must never be used in alkaline environments. Because of these properties, silica refractories are widely used in acid furnace applications, especially in glass production and in acid slag steel furnaces. Next, let's talk about fire clay refractories, one of the most widely used refractory materials worldwide. Fire clay refractories are essentially hydrated aluminum silicates. In simple terms, they are made from a combination of aluminum oxide and silicon oxide, along with small amounts of other minerals. The typical composition is less than 78% silica and less than 44% alumina. This balance gives fire clay refractories excellent thermal properties and good chemical stability. Fire clay bricks are classified into 5 duty levels based on performance. Super duty are the highest grade, for the toughest conditions. High duty, excellent performance in demanding applications. Semi-silica, intermediate performance. Medium duty, moderate performance. Low duty, a basic performance for less demanding uses. In India, several standards define these grades. Indian Standard 9010, 1978, Super Duty Fire Clay. Indian Standard 8, 1994, High Duty Fire Clay, divided into Type 1 and Type 2. Indian Standard 6, 1983, Moderate Heat Duty Fire Clay, divided into Groups A and B. Because of their balance of performance and cost, fire clay refractories are the most widely used refractory materials globally. They provide reliable service in a wide range of industrial applications without being prohibitively expensive. Now let's move on to alumina refractories. These refractories are made from aluminum oxide and silicon oxide, but what sets them apart is that they contain at least 50% alumina. That higher alumina content gives them superior performance compared to regular fire clay refractories, especially at high temperatures. Alumina refractories are classified into 7 groups based on alumina percentage. Class 1, 50% alumina. Class 2, 60% alumina. Class 3, 70% alumina. Class 4, 80% alumina. Class 5, 85% alumina. Class 6, 90% alumina. Class 7, 99% alumina. Ultra-high purity. As the alumina content increases, so do the temperature capability, strength, and cost. So, the choice depends on balancing performance requirements with budget constraints. Because of their high strength and heat resistance, alumina refractories are essential for demanding applications like steel furnaces, electric furnaces, and high-temperature industrial kilns. Now let's look at magnesia refractories. These refractories are made primarily from magnesium oxide or MgO. Because of their chemistry, they are classified as basic refractories, meaning they perform well in alkaline environments and resist attack from basic slags. Magnesia can be sourced in several ways, from brines, saltwater solutions often drawn from deep wells, from seawater which contains significant magnesium, or from synthetic magnesia that is sintered or fused at high temperatures. Magnesia refractories are especially important in steel-making furnaces, where the slag is basic. In these conditions, acidic refractories would quickly fail. But magnesia refractories resist chemical attack and remain strong even at very high temperatures. There is one limitation to keep in mind. Magnesia refractories are sensitive to moisture. If exposed to humid conditions, they can absorb water and hydrate, which damages their properties. That's why proper storage and handling are essential. In short, magnesia refractories are a cornerstone material for steel furnaces and other basic slag applications, provided they are carefully protected from moisture. Now let's talk about dolomite refractories. These refractories are made from magnesium oxide and calcium oxide, produced from sintered dolomite, a mineral that naturally contains both magnesium and calcium. Like magnesia refractories, dolomite refractories are classified as basic refractories, which means they perform well in alkaline slag environments. Their big advantage is that they offer good performance at a lower cost, making them a more economical alternative to pure magnesia in many applications. But there's one important limitation. Dolomite refractories are sensitive to moisture. If exposed to humid conditions, they can absorb water and deteriorate. That's why proper storage and careful handling are essential to maintain their properties. In short, dolomite refractories provide a cost-effective solution for basic slag environments as long as they are protected from moisture. Now let's look at chromagnesite and magnesite chromite refractories. These materials combine magnesium oxide, MgO, with chromium oxide, CrO, giving them unique properties for high-stress applications. In chromagnesite refractories, The composition typically includes 15 to 35% chromia and 42 to 50% magnesia. In magnesite chromite refractories, the balance shifts. The material contains at least 60% magnesia and 8 to 18% chromia. The choice between the two depends on the specific application and performance requirements. What makes these refractories special is that they combine the excellent slag resistance of magnesia with the superior thermal properties of chromite. This makes them ideal for extremely demanding conditions, such as lumley linings and other critical parts of steel-making furnaces. One important note: chromite-containing materials can leach chromium under certain conditions. That means proper handling and environmentally responsible disposal are essential. In short, chromagnesite and magnesite chromite refractories deliver strength and reliability in the toughest steel-making environments, but they must be managed carefully. Next, let's explore silicon carbide refractories. These are produced from silicon carbide, a synthetic material created in a resistance-type electric furnace at temperatures above 2500 degrees Celsius. The process involves reacting silica with carbon at these extreme temperatures, resulting in a material that is incredibly hard, extremely strong, and has outstanding thermal conductivity. Silicon carbide refractories deliver remarkable performance. They are chemically stable, conduct heat efficiently, and maintain mechanical strength even at very high temperatures. But there is one critical limitation. In oxidizing atmospheres, silicon carbide can begin to oxidize at temperatures above about 1700 degrees Celsius. This oxidation can reduce performance and must be considered when selecting materials. Because of their unique properties, silicon carbide refractories are used in specialized applications where strength, conductivity, and stability are essential, such as heating element cores and specific furnace zones. However, they are not suitable for every environment. In short, silicon carbide refractories are high-performance materials for targeted applications, but their use must be carefully matched to operating conditions. Finally, let's look at zirconia refractories, premium performance materials designed for the most extreme high-temperature applications. The main constituent here is zirconium oxide, or ZRO. Zirconia refractories are especially valuable as construction materials in environments where temperatures exceed 1900 degrees Celsius, conditions where conventional refractories simply cannot survive. They're used in highly specialized applications such as casting nozzles and gates for metal casting, crucibles for ultra-high temperature processes, furnace liners, and kilns operating at extreme temperatures. One unique property of zirconia is its low thermal conductivity compared to most other refractories. This makes it useful not only as a structural material at extreme temperatures, but also as a high-temperature insulating refractory. The main limitation, however, is cost. Zirconia refractories are very expensive, so they're typically reserved for critical applications where performance justifies the premium price. In short, zirconia refractories deliver unmatched reliability in the harshest environments, but they come at a high cost, making them a specialized choice for only the most demanding situations. Now let's explore carbon refractories. As the name suggests, their main constituent is carbon. But carbon can exist in several forms: formed carbon, which is pre-shaped, manufactured carbon, created synthetically, amorphous carbon, which has no crystal structure, and baked carbon, produced through thermal treatment. Carbon can also be processed into graphitized form, where it's converted into graphite at very high temperatures, or into semi-graphitized form. Here's what makes carbon refractories remarkable. They have an extremely high refractoriness, meaning resistance to melting, and a very high softening temperature under load. In simple terms, they can withstand heat levels that would melt or weaken most other refractories. They also resist the action of slags and maintain excellent thermal stability. But there's a critical limitation. Carbon refractories are suitable only in reducing environments, conditions where oxygen is absent or minimal. In oxidizing environments, carbon would burn or oxidize away, making these refractories unsuitable. That's why carbon refractories are used in very specific applications, such as blast furnace hearths and crucibles, where reducing conditions are guaranteed. In short, carbon refractories are unmatched for extreme heat resistance, but only when oxygen is kept out of the picture. Refractories can also be classified based on the manufacturing method used to produce them. There are several primary methods, each giving the material different properties and performance characteristics. Dry press process. Here, dry or slightly moist material is pressed into shape using mechanical presses. Fused cast process. In this method, the material is melted at extremely high temperatures and then casted into shape. Hand molding process. Material is shaped manually, often for custom or specialized applications. Forming processes, which can include normal forming, fired forming, or chemically bonded forming. Unformed refractories. These are not manufactured into finished bricks but applied directly. Examples include monolithic materials, plastics, ramming masses, gunning materials, and castables. Each manufacturing method produces refractories with different properties, cost profiles, and performance levels. The choice of method depends entirely on the desired final properties and the specific application requirements. In short, how a refractory is made is just as important as what it's made of, because the manufacturing method directly shapes its strength, durability, and suitability for different industrial uses. Refractories can also be classified based on their principal base features. In other words, the fundamental chemical nature of the material. Broadly, there are two main categories. The first is oxide-containing refractories. These are based on oxides and their compounds, and they form the backbone of most traditional refractory materials. The most important oxides here include aluminum oxide, calcium oxide, magnesium oxide, silicon oxide, chromium oxide, zirconium oxide. These oxide materials make up the majority of refractories used worldwide. They are well understood, proven over decades of service, and trusted in countless industrial applications. Oxide refractories offer a strong combination of excellent performance, reasonable cost, and broad availability, which is why they remain the most widely used category in industry today. The second major category of refractories is non-oxide refractories. These represent advanced materials designed for specialized, high-performance applications. Examples include carbon-based refractories, carbon and graphite materials used in reducing environments. Carbides, such as silicon carbide and other carbide compounds. Nitrides, including boron nitride, silicon nitride, and related compounds. Borides are compounds containing boron. Silicides, compounds made from silicon and metals. Sialones, a family of advanced materials derived from silicon nitride. Non-oxide refractories offer unique properties that oxide refractories simply cannot provide. However, they are usually more expensive and their applications are limited to situations where those special properties are absolutely necessary. Today, the refractory industry is actively developing new non-oxide materials to meet the needs of advanced manufacturing and extreme environments. In short, non-oxide refractories are the cutting-edge option, selected only when performance requirements demand their unique characteristics. Refractories can also be classified based on their compactness, that is, their density and porosity. There are two main types. Dense refractories, these have a true porosity of less than 45%. They are compact, solid materials that provide strength, durability, and protection. Because of their low porosity, they resist penetration by heat and corrosive gases, making them ideal for the hot face of furnaces. Insulating refractories, these have a true porosity greater than 45%. Their high porosity gives them excellent thermal insulation and makes them lighter in weight. They are often used as backing materials to reduce heat loss and improve energy efficiency. The choice between dense and insulating refractories is a fundamental design decision. Do you prioritize strength and thermal protection, or do you prioritize insulation and energy savings? In practice, most furnace designs use a combination of both: dense refractories on the inside, where they face the highest temperatures, and insulating refractories behind them to conserve energy. Another way to classify refractories is by their fusion temperature, the point at which the material begins to soften and melt. This classification divides refractories into three categories: normal refractories, with fusion temperatures between 1580 and 1780 degrees Celsius. Fire clay refractories are the classic example here. They're widely used in standard industrial furnaces operating at moderate to high temperatures. High refractories, with fusion temperatures between 1780 and 2000 degrees Celsius. Chromite refractories fall into this group, extending performance into higher temperature ranges where normal refractories would start to soften. Super refractories, with fusion temperatures above 2000 degrees Celsius. Zirconia refractories are the prime example. These are reserved for extreme high-temperature applications where no other material can function reliably. Fusion temperature classification is critical because it ensures you select a refractory whose melting point is safely above your operating temperature, typically by 200 to 300 degrees Celsius. That margin guarantees long-term reliability and performance in service. In short, knowing the fusion temperature helps engineers match the right refractory to the heat demands of the furnace. Congratulations! You've just completed episode 2 of Refinery Pro, Classification of Refractory Materials. By now, you understand the major classification systems by physical form, chemical properties, chemical composition, manufacturing methods, principal base features, compactness, and fusion temperature. We explored shaped refractories like insulating bricks, dense bricks, and specialty shapes, as well as unshaped refractories such as castables, moldables, and ramming mixes. We also looked at ceramic fiber materials and backup insulation options. You've learned the chemical nature of acidic, basic, neutral, and special refractories, and you're familiar with the 9 chemical composition categories, each with its own unique properties and applications. In our next episode, we'll move from classification to properties of refractory. If you found this series helpful, don't forget to subscribe to Refinery Pro and share this episode with colleagues and peers in the industry. Thank you for watching, and stay connected, because the best is yet to come.